This is a lecture by Alemi, narrated by Buttar. This lecture focuses on the methods of accurately assessing low probability, high consequence events. The methods include fault trees, similarity judgments, importance sampling, and time to the event. In general, there are two ways of assessing probabilities, both of which are not reasonable for assessment of rare events. The most common approach is to rely on observed frequency of the event. This method cannot be applied to rare events, as by definition, rare events do not occur often, and one has to accumulate a large data set before reliable estimates can be made. For an event that occurs once a decade, one has to collect several decades of data before a reliable estimate can be obtained. Clearly, this is not practical for most risk analysis efforts. Alternatively, many rely on experts to assess probability of events, but human beings are notoriously ill-equipped to distinguish among very small probabilities. In estimating rare probabilities, sometimes orders of magnitudes are missed, and probability of 1 in a million is estimated as 1 in 1,000. An alternative is needed that overcomes difficulties in estimation of rare probabilities. There are a number of methods available for assessing probability of rare events. This review discusses 4 approaches: use of fault trees, similarity judgments, importance sampling, and time to the event. Each of these approaches are further discussed below. The concept of fault trees and reliability trees has a long history in space and nuclear industry. Several books and numerous papers describe this tool. The first step in conducting fault trees is to identify the sentinel adverse event that should be analyzed. Then, all possible ways in which the sentinel event may occur is listed, and the probability of each pathway is assessed. Finally, the calculus of probability is used to combine information from various pathways. If several events can independently cause the following event, the so-called quote-unquote OR gate, the probabilities of these events are added to each other. If several events must occur before another event can follow, the so-called quote-unquote AND gate, then probabilities of these events are multiplied by each other. For example, in assessing the probability of privacy violation in our hospital, 2 events independently may lead to privacy violations: the network penetration and SAME of information by an employee. In a fault tree, the impact of independent causes is tracked through an OR gate. Each of the 2 causes of privacy violation anticipated in this image may have different prerequisites. A network penetration occurs if there is a weak access control and a hacker is interested in access to the information. For an employee to sell information, several events must occur. First, the employee must be disgruntled. Second, information must be available to the employee. Third, outsiders must have contact with the employee. Fourth, the employee must have a method of transferring the data. All of these events must co-occur before hospital data is sold to an outside party. None of these events are sufficient to cause a sentinel event. In a fault tree, when several events must co-occur, we use an quote-unquote AND gate. Fault trees is a collection of events connected to each other by quote-unquote and quote-unquote OR gates. Each event depends on a series of other related events, providing for a complex web of relationships. A fault tree suggests a more robust work environment when several events must co-occur before the catastrophic failure occurs. The more quote-unquote AND gates are in the tree structure, the more robust the process modeled. In contrast, it is also possible for several events by themselves to lead to catastrophic failure. The more quote-unquote OR gates in the path to failure, the less robust the work process. After organizing the fault tree, the probability of each node with no prior input is assessed, and the calculus of probability is used to assess the probability of the rare event. Since the catastrophic failure is rare, it is difficult to assess the probability directly. Instead, the probability of various events leading to this failure are assessed. In this example, we have estimated the probability of finding a disgruntled employee, probability of an employee having access to private information, probability of an employee having access to a purchaser of private information, and the probability of the employee having access to means of transfer of the data. Similarly, we assess the probability of a weak network control and a hacker having interest in penetrating the system. These estimates, while difficult to make, are not rare. From these, we have estimated the probability of privacy violation. Note that the probability of privacy violation is estimated to be 0.0006, a very small number, though the probability of the various elements contributing to it is relatively high. This example demonstrated how the probability of rare events may be estimated from a series of causes and constraints of the rare event. Exercise. Assess the risks for privacy violations with estimates from peer students. Please use the course website to ask a question and rate this lecture. This lecture will continue with a presentation on similarity judgments.